In this simple truss problem, we're asked to determine the force in members GF, GD, and CD of the truss, and to state if those members are in tension or compression. So when we have a truss problem and we're asked to find the force in specific members, that's a pretty good sign that we're going to want to use the method of sections. You don't have to. You can use the method of joints, but normally the method of sections is going to be a more efficient way to work the problem. I'm going to use the method of sections here. And the first thing I'm going to do is to decide how to cut the truss. So they asked for the force in these three members, GF, GD, and CD. So if I take my cut through those three members, I will have created three unknowns, which I generally don't want to cut through more than three members or create more than three unknowns. There'll be too many unknowns for the equations available. And by cutting through those members, I will have cut the truss entirely into two pieces. So let me do that cut here. Okay. Now the second step is to determine which side of the cut is going to be easier to work with. So I look at the right side of the cut and the left side of the cut, and I see that on the left side I'm going to have two unknowns at A, potentially the y and x, the x and y components of the reaction force at A. I've got two forces on that side, whereas on the right side I'm going to have a vertical reaction force at E and just one applied load. So again, you could choose either side here, but I'm going to choose the right side. It looks like the easier side to work with. Now I'm going to need the reaction force at E when I draw my free body diagram of the right side of the cut. So I'm going to solve for that now. I'm going to take a little shortcut. I'm not going to draw the free body diagram of the entire truss. I'm not going to redraw the truss. It would not come out well on the iPad here. So I'm going to, I'll put it in purple here. I'm going to just use the existing figure for my free body diagram. So I would need to remove the truss from the supports, the two supports. Okay, and show I'll just call this E, and I'll call this A sub Y and A sub X. And I'm going to solve for the force E by summing moments about A. It's rigid body equilibrium, so I can write a moment equation that's equal to 0. And I'm going to pick up all of the moments of the applied loads plus the support reaction at E. So I'm going to have minus 10 times 2 meters, minus 25 times 4 meters, minus, minus 15 times 6 meters, plus E times 8 meters. And I solve that for E and get that E equals 26.25 kilonewtons. Okay, now I can draw my free body diagram of the right side of the cut. So I'll do that. I'll do that over here. Okay, so I have a, make this D, this E. Put D there. And then let me draw this one, where this is F. Connect these two. And then I want to show my cut members. So I'll have a force, and I'm going to assume all of these cut members are in tension. I'm going to have FGD. And I'm going to have FGF. Let me put that F here closer to the joint. Okay, so I have my showing my unknowns there. Now I need to show my given applied loads. So I have a 15 kilonewtons applied at D, and that reaction force at E was a positive 26.25 kilonewtons. Okay, and some geometry. This is 2 meters. This is 2 meters. And if we look back at the dimensions on the truss, this FCD has a slope triangle with sides of 2 and 3, which is going to make the hypotenuse root 13, and FCF had a slope triangle with sides 1, 1, and 2, which makes the hypotenuse root 5. Okay, so I'll call this FBD of right side of cut. Okay, now I'm going to apply my equations of equilibrium. Now, unlike the method of joints, this piece of the truss is a rigid body, so it's rigid body, 2D rigid body equilibrium. I have 3 equations available to me, some of the forces in the x direction, some of the forces in the y direction, and some of the moments about any point. All of those I can set equal to 0 since the rigid body is in equilibrium. And normally on these, you're going to write a moment equation first and that you'll usually find that writing a moment equation about some point will let you solve for one of the unknowns directly in that equation. So let's look at where we could sum moments to pick off one of these unknowns. And notice that if we sum moments about D, that the two unknowns acting at D will not be involved in that equation because they act through the point. And E is known. The 26.25 kilonewtons is known. The 15 kilonewtons is also not going to be involved. And the only unknown that's going to be involved in that equation is FGF. So let's do that and sum moments about D. Okay, and we'll have 26, well, equals 0. We'll have 26.25 times 2 plus FGF, the x component of FGF, so we're going to multiply FGF by 2 over root 5. And then its moment arm is going to be 2 meters. Okay, and if you do that math, solve for FGF. Obviously, FGF is going to come out negative. FGF equals negative 29.35 saw a little text there, but not too much personal information revealed. 29.35 kilonewtons negative, which means that FGF equals 29, I'm going to round that to 29.4. 29.4 kilonewtons compression. Okay, again, I assumed all my unknowns are in tension. When I see that negative sign, I know that that automatically means compression because I've assumed that my unknowns are in tension. And I don't have to double think it, triple think it. I just know it's compression. Okay, so I've solved for FGF. Now I can sum forces in the y direction. And now here's where you have to be a little careful. I'm going to take the y component of FGF here, and I need to realize that FGF is acting in compression. It's acting opposite the way it's drawn on my free body diagram. So you have to keep track of this. So it's going to be minus 29.35 times 1 over root 5 plus FGD times 3 over root 13. The numbers weren't the standard 3, 4, 5 or 5, 12, 13, but you know, and I just usually leave them as radicals rather than until the end, rather than have to write all those numbers down. Okay, minus my 15 kilonewton force at D plus the 26 0.25 kilonewton force at E. And I do that math, and I get that FGD equals 2.25 kilonewtons, which is positive, so that's tension. And then I write my last equilibrium equation. Now again, I need to realize that for FGF, it's actually acting downward and to the right, so its x component is going to be a positive 29.35 times 2 over root 5. And now I need the x component of FGD, and FGD is in tension, so it's acting to the left and upwards like it's shown on my free body diagram. So the x component of that is going to be minus the magnitude of FGD times 2 over root 13 minus FCD, which only acts in the x direction. And I do that math, and I get FCD equals 25.0 kilonewtons. And that's positive, so that's in tension. And actually, to keep these straight, I should be putting parentheses around them so you don't get them mixed up with your units. Okay, so different than the method of joints. Method of joints definitely has its place, but method of sections does also and can save you a lot of time for certain types of problems.